All right, well, thanks for coming. Let's get lazy. That's what I'm going to talk about. How many of you here are lazy? Yeah, that's what I figured. Absolutely, I'm in the right group. Well, I'm absolutely lazy. If you look at the dictionary for the meaning of the word lazy, my picture is actually there. I'm absolutely lazy, but lazy actually means efficiency. That's what I want to talk about in this presentation. We're not going to use any slides. I'm going to just rant away, talk about stuff, write some code. If you have any questions, best time to ask your questions is whenever you have it. So please don't hesitate or wait till the end. Anytime is a good time to ask questions, just fire away, draw my attention, and speak up. So let's talk about what does it really mean to be lazy. So I'll talk a little bit about laziness. I'll talk about why it's important to be lazy, and then we'll talk about how we can actually achieve laziness in different languages. I'm going to use a mixture of languages in this presentation. I'll show just a little bit of Haskell, a little bit of Scala, and then I'll jump into Java and look at some Java examples as well. So let's get started. So what does it really mean to be lazy? Well, laziness really is about postponing evaluation. Sometimes we call this as deferred execution. And the reason for deferring execution is really to say that we don't want to be doing stuff that really doesn't have to be done. Let's take a look at an example for a minute. Imagine January the 2nd, the boss calls you and says, I've got an important project for you to work on, and the report is due on April the 15th. So at 2nd January, you come back to your desk, and you immediately start working on that project, right? No, that's what I figured, right? You will promptly start it on April the 14th because it's due on the 15th, isn't it? In fact, there's something you know the boss doesn't know. You plan to quit on March the 1st. Why in the world would you spend your time on this project anyways, right? Well, what is that called? That's called being smart, isn't it? And this is exactly the point is we don't want to do stuff until we know for sure there is a reason to really do it, that it'll be used, and otherwise you want to postpone it. Well, that's exactly the reason for postponing evaluations. When it comes to programming languages, there are some differences in how functions are evaluated in these languages. These are often called as applicative order versus normal order. It's really funny these terms are being used because normal order is actually that's not that normal. It's somewhat abnormal. Most programming languages actually use what's called the applicative order, and the word applicative order simply means it is applied or invoked or executed when you are really calling it. On the other hand, normal order is quite different. So like I said, most mainstream languages use applicative order rather than normal order. Let's take a look at an example of what this really means. Let's jump into a little example with Haskell for a minute. Haskell is one of the probably the best known functional programming languages, and functional programming languages are inherently lazy in their evaluations. This is one of the reasons why I really get excited about laziness is because we're getting more and more excited about functional programming, and laziness is a very important aspect of functional programming. Let's talk about this for a second. Let's say we have a function called add, which takes A and B and returns A plus B. So that's a very simple add function here in Haskell, nothing really exciting about this. Then I write a method called evaluate, and the evaluate function takes a value and returns a value. So that's also a fairly simple function here as well. Then I'm going to write a function called main, and in the print I'm going to call evaluate, and then I'm going to call add 1 and 3 over here and ask it to execute the little code. Now what does Haskell really say? Haskell says the result is 4. But what is really exciting about this is not what you see, but what's actually happening behind the scenes. You go to Haskell and say, Haskell call add, and Haskell says, why? Well, because I'm going to send it to evaluate. Haskell says, then go call evaluate, why are you wasting your time? Then you go to Haskell and say, call evaluate, and Haskell says, but why? Well, because I'm going to send it to print, and Haskell says, okay, that's a good reason, because print is going to print it. So the way Haskell actually works with this code is not what you would expect. If this was Java code or most of the languages we normally use, add will be called to begin with. And the result of add will be passed to evaluate, and the result of evaluate will be passed to print, but not so in Haskell. Well, how do I really prove that? I'm a person who always says, prove it. Show it to me, just don't talk about stuff. Well, I'm going to prove something that's obvious here, and that is that add is actually being evaluated. Not very helpful example, but let's nevertheless spend some time on it. So here's what I'm going to do to prove it. Well, unfortunately, when I sat down to prove this, I was in a bit of a shock. Because you cannot go to Haskell and do something like what you would do in language like Java and C and C++ and various other languages, which is to say print called, and at this point Haskell will stare at me and say, are you serious here? Because this is called a side effect. In Haskell, functions don't have side effect unless you specifically ask the function to have a side effect, so I cannot quite call the print method here. So I was sitting there and scratching my head, how do I prove this stuff? I never thought I would use a debugger to prove something. So in this case, I'm going to bring up GHCI, which is the REPL for Haskell, just like JShell in Java now. And I'm going to say, load this sample.hs, that particular file. I've loaded it. Once I've loaded it, I'm going to say breakpoint. I'm going to put a breakpoint right here on line number 1. And I'm going to put the breakpoint on character number 16, which is the end of that particular line. So I'm going to ask you to put a breakpoint on line number 1. And at this point, once I put the breakpoint on it, what do I want to do? I want to ask it to go ahead and execute the method main. And notice that it's actually waiting for us right there within the add method. So right there you can see we are in the add method. It's waiting with the data 1 and for A and 3 for B. That's a proof that we actually stepped into the add method. Of course, you could say, Venkat, you didn't have to prove it so hard because it did print a value of 4. Okay, I get that, but still, nevertheless, we proved we got into it. Now I say continue right here, and you can see the result of 4. So I took all that pain to show you what's really obvious. However, let's make a slight change to this code. I'm going to return a 42 right here. Now when I run the code, notice it printed 42. Once again, let's go to Haskell and see what it does. Use a Haskell call add. It says, but why? Well, because I want to pass it to evaluate. Well, then go call evaluate. Why do you bother? Okay, call evaluate. It says, but why? Because I want to print the result. Okay, that's a good reason to call the evaluate method. So you call the print, and that takes on evaluate. And then, of course, evaluate simply returns 42, totally ignores the value. So why waste the time really doing what you don't have to do? So the add is never really called at all. Of course, you say, prove it. Well, exactly why I wanted to go through that exercise a few minutes ago. So let's bring up the REPL again. Let's load the particular program. Let's set a breakpoint exactly where we did last time. Now let's call the main function. Notice it never, ever entered the add method. That is an example of what is called a normal order. So in other words, Haskell says, I don't need to evaluate functions unless the result of the function is going to be used. And if a result is never going to be used, why bother wasting the time doing all that execution? That's pretty pointless, isn't it? That's exactly what we saw here. Let's continue a little further. Some normal evaluation or normal execution or normal order of execution is rather very uncommon. Not a lot of different languages do this. Haskell does this pretty effectively, but a lot of other languages don't. You may, I'm a why kind of a person. I always ask the question, why? And the reason for that is in Haskell, every single function is considered to be pure unless you mark it exclusively as impure. In a lot of other languages we normally program in, functions are usually impure. They cause side effect until you take the pain to emphasize it's actually pure. So these are actually two extremes of what I call as defaults, safe defaults versus unsafe defaults. I'm not complaining, but I'm just observing here. Language like Haskell has a safe default. Everything is pure unless you say otherwise. Language like Java, on the other hand, it's unsafe default. Everything is impure unless you take the effect to say it's pure, like marking things as final. This makes a very big difference in how languages can deal with things under the hood. So some languages are born lazy. They're born at the beach. They don't do anything really, just hang in there and have a good time. But in some languages, you have to work really hard to be lazy. It's kind of like me. I'm always kind of hyperactive, doing something or the other. And my wife will say, why don't you relax? And I'm like, how do you do that, right? And some are like that, always active and hyperactive, really hard to become lazy and relaxed. Well, but we have to work a little hard to be lazy in some other languages. Let's take a look at an example real quick and play with it. So let's switch gears here to a little bit of an example in Scala. Well, let's say we have a function here. I'm going to call it as compute, where the function compute takes an integer value as an input. And all it's going to do is return n times 2. Let's keep it extremely simple and trivial. Now I'm going to say x is equal to 4. Then I say, if x is greater than 5 and compute of x is greater than, let's say, 7, I want to really print out here, let's call it as path 1. Otherwise, I'm going to simply print out over here, we'll call it as path 2. So a very simple example, as we can see here, we have a compute method which is returning the n times 2. A val is 4. If x is greater than 4, then of course, a compute is greater than that, print path 1, otherwise print path 2. Well, obviously, I want to run this code and see what it's going to return to us. And as I execute this little program, the output says path 2. So that's not a surprise. We clearly know that's what the output is going to be. But the question really is, if I come here and say, let's say called, my question is, will the compute be called, is the question. What do you think? I'll give you a clue, yes or no. What do you think? Will compute be called or would not be called? No, of course not. Why not? Bingo, short circuiting, right? Everyone knows about short circuiting. There's not a programmer in the world who doesn't know short circuiting. Moms feed their children when they're babies and teach them about short circuiting to say, kid, when you grow up one day, when you start programming, you better know about short circuiting. Anyone knows who created short circuiting? Yeah, that's been the puzzle, right? It's been a very long time since John McCarthy introduced this as part of Lisp programming language way long ago. This is one of the reasons why it's a foregone conclusion. Every single language implements short circuiting. So when I execute this code, clearly compute was not called, and everybody in this room knows it, everybody in the world knows it when they start programming. But on the other hand, I'm going to make a small change to the code. I'm going to put temp over here. And then I'm going to say val temp is equal to compute. I'm going to run the code in a second, but it's a very small change. Well, syntactically, we moved this around to a compute method up there, and then stored the variable result into a temp and use the temp over here. My question to you, is compute going to be called now? I heard the word yes. Let me rephrase the question to a slightly different question. Should the compute be called now? What do you think personally? No, right? Absolutely. What a waste. We know compute is not going to be used. Why bother calling? You say no, but the language says yes. And why did the language decide to call this method? This really comes down to what is called language specification. When it comes to language specification, you can never argue with it. It is whatever the language says it'll do. Every language says, in a short-circuiting situation, we reserve the right not to call the methods. And so languages just completely discard calls when it's short-circuiting. On the other hand, if you execute a method in isolation and store the result into a variable, the same languages say, oh my gosh, what if you are performing a side effect? What if you are updating a database? What if you're logging? What if you're changing other things? And if I don't call that, you'll be upset. I'm going to call it. Well, again, this comes to language specification. If you read the specification of languages like C++, it's really interesting how clearly they say, if your constructor were to cause a side effect, we may not call your constructor, even if it causes a side effect, in cases where we determine there's no point in creating this object. So languages can give these kinds of clauses to exclude themselves from calling methods, even if they have side effects. Obviously, if the language knows your function doesn't cause any side effect, then it can exclude the call. But if the language doesn't know that you're causing side effect, they're going to fear the worst, that you're causing side effects. Now, obviously, the question here is, you're saying, oh, Venkat, but this method should not have been called, but unfortunately, in this case, Scala actually called it. Well, what you can do here in Scala is, you can mark this particular variable as lazy. Now that I marked it as lazy, when I execute the code, notice it did not call the method at all. Once again, let's try this. Without lazy, you see that the method was called, marking this as lazy, you can see that it completely avoided calling that. So this is again coming back to the language semantics. Languages can tell you, oh, just mark me as lazy. If that variable is really not being used, then I would not really perform that operation. But if the variable is actually being used, then I will call it. Once again, you can see how we can start using some of these in languages to gain on some performance by eliminating calls that shouldn't be executed otherwise. Let's switch over to Java for a second. In Java, I'm going to do the same thing again here. Let's call the method as compute right here. I'm going to take a value n, and I'm going to simply return n times 2, just like what we did a minute ago. Let's say in this case, int x is equal to 4, and I say if x is greater than 4 of 5 and compute of x is greater than 7, I want to print out, let's say, path 1. Otherwise, I'll simply print out right here, let's call it as path 2. Once again, when I execute this code, we can see that in this particular case, the result of this particular call is going to tell us whether the path 1 or path 2 was evaluated, as you would see in this particular case. So when I run this little code, you can see it's path 2. But going back to this code one more time, I'm going to output right here, and I say called, and you would notice that the call was never actually called thanks to short circuiting. So in this case, Java behaves just like what you would expect any language to behave in the case of short circuiting. But on the other hand, I'm going to come down to this code and say that int temp is equal to compute, and in this case, I'll pass the value of x, and then I'm going to go ahead and put the temp over here. When I run this code, you will see Java did call the compute method, because just like Scala did, Java says, what if the method were to cause a side effect? I better call it. So what if you can simply say lazy over here and ask it to execute? Well, except it doesn't work. For a minute you thought there, right? You're like, yes. Well, I'm sorry to disappoint you, but Java doesn't quite have it. Well, Scala has lazy. Java doesn't have lazy. If you really want laziness, if you look at languages like C#, they have lazy as well. Well, Groovy has an annotation for lazy. So in Groovy, you could actually say lazy, and you can mark it as an annotation. If you're interested in doing something like that in Java, take a look at Project Lombok. Project Lombok gives you annotations to do very similar operations. And if you're interested in using an extra library in your project, you can attain laziness using things like Lombok. But then you say, wait a minute, I don't want to use any extra libraries than what's in Java. How can I really attain laziness? Well, let's talk about eager versus lazy evaluation a little bit further. Then we'll talk about how we can postpone some evaluation. So eager evaluation is where you evaluate something the minute you are given. On the other hand, lazy evaluation is where you postpone evaluation until you think about the consequence of the call you are making. So how do you really get to lazy evaluation? How can you postpone evaluating something? Well, in order to understand that, we are in a language like Java. How do we really postpone evaluations? For this, I'm going to invoke the words, probably the best words ever spoken, hands down, in computer science. In fact, I would say if a special prize were to be given for the wisest words spoken in computer science, I would argue it should go to the gentleman named David Wheeler, because he said something that I think of every single day when I program. Because it's so profound, he said, in computer science, he said, we can solve almost any problem by using one more level of indirection. What a beautiful, beautiful way of thinking. I would say this is probably one of the most important things we can ever learn in our field. Why is this so important? The level of indirection absolutely rules the way we write code. So what is level of indirection? Rather than you doing a piece of work, you call a function that will do the piece of work for you. In a way, if you really think about it, eager evaluation is where you're immediately calling a function. What if I can postpone calling that function? Well, think about it this way. Imagine I have an apple with me, and not my Apple computer, but an apple, a fruit. And imagine I give you an apple. Well, there are 4 things you can do with this apple that I give you. You can eat it right away if you're hungry. That's perfectly fine. You can save it for eating it later during the break. You can give it to the person next to you. or you can throw it in the trash can, right? So there are 4 things you can do when an apple is given to you: eat it right away, eat it later, give it to somebody else, or throw it away. Which is exactly the point. What's that apple that I'm talking about? That apple in programming is called lambda expression. So what does a lambda expression really provide? A lambda expression is a level of indirection. This was my aha moment when I started programming with lambdas. It took me a while to figure this out, but one day I jumped out of my seat and said, that's amazing. Lambdas are a level of indirection. Why? Because when you create a lambda expression wraps around another expression. You can either call that expression right away, you can call it later, you can pass it to something else, or you can just throw it away. So in other words, you can apply a level of indirection in programming by using lambda expressions. Once you get the wind of it, it changes the way you think about design. So just because the language doesn't offer laziness doesn't mean we cannot really implement laziness, because with the ability to do lambda expressions, we can bring in laziness quite effectively. Let's take a look at how we could probably implement laziness in our code here. So I don't want to call compute right now. I want to postpone calling compute. How would I do this? Well, that's where we are going to bring in this lambda expression as the level of indirection. So rather than really using compute directly, wrap the compute within a lambda expression. The lambda is evaluated, but the lambda is not executed. There's a difference between the two. A lambda being evaluated simply says, this lambda is actually legal, it's doing the right things, its syntax is proper, and we're ready to run it when you want me to run it, but it's not going to be evaluated until a much later time. So how do we really bring that together? Let's give it a try right here. I'm going to go back and look at a few interfaces we can actually use. The first interface here is, there are 4 famous interfaces in the case of Java. So what are the 4 famous interfaces? The first famous interface is consumer, right? This is a functional interfaces. What does the consumer do? It takes whatever you give it. It never returns anything back to you. I often say consumer is like my government. I always send money, nothing comes out really. So consumer just swallows everything you give to it. That's what a consumer is for. The second most famous interface is called predicate. A predicate returns a true or false for any input you provide for it. The third famous interface is the function interface. This takes an input and returns an output, much like a predicate is, but except this could be any output, not just Boolean. The fourth one, which is probably the less known of the 4, is called the supplier. I call the supplier as the mother's love. She always gives you stuff, never expects anything in return from you. That's basically what a supplier really is. A supplier is a really good candidate to use for lazy evaluations, and that's exactly what I'm going to do here. So notice what I'll do here. I will turn this code that we have right here in front of us into using a supplier of integer, and we'll call it as temp is equal to. Rather than calling compute of x right here, let's wrap this into a lambda. Notice the level of indirection that I'm introducing right there. So what I just did is, rather than calling compute right away, I'm actually creating a lambda expression, which will in turn call the compute. So in other words, that right there is a level of indirection. So we have taken this function compute, and rather than immediately running to call it, we wrap into a lambda and say, here you go, that's the lambda for you. Don't be in a rush, you can call it later on. So now that we wrapped it into a temp, we can then come down here and say a temp.get to get the value out of it, and we can execute it. Now when I run the code, notice it did not call the compute method. On the other hand, if I said if x is greater than 3, you can see that it's calling the method. But if I said if x is greater than 5, it's not calling the method, even though the lambda has been created up there. So in other words, by using a lambda expression, you can introduce a level of indirection. Okay, clearly there's one small problem in this code. If you try this in language like Scala, the lazy will actually evaluate the method only once. But in this example, every time you call get, that method is actually going to be invoked. Well, you can put a little bit more code around it to eliminate that by caching the results For that, you have to put a little bit more effort in writing the code, and you can play with it. For example, again, I would say using something like Project Lombok will save the effort for you, but if you want to create something like this all by yourself, you could try something like this. You could create a class called lazy, and within the class lazy, you might be saying it's of type T, whatever the type T is, and you could say this is the object that you are really interested in creating, and you want to store it away. Then you could say supplier of T in this case. So I could create a supplier of T, and let's call it as supplier that I'm going to store it away. Then we'll create a public method right here, the constructor rather. And what does this take? It takes a supplier, we'll call it the supplier right here. And then once a supplier is given to us, let's store it away, supplier equal to the given supplier. Then we can say a public T get, and the get method can say if object is equal to null, where the object doesn't exist, object is equal to the supplier.get, get it from the supplier, let go of the supplier, we don't need that anymore, and then simply return the object given to us. So what we could do here is we could create our own homegrown laziness. As you can see, we are doing a little bit extra work to be lazy, but you could tuck this away into a library of functions or methods or classes for reuse if you really wanted to. So the lazy T says, I'll store an object of type T, I'll store a supplier. When you create me, give me a supplier. When you ask for the object, if the object doesn't exist, I'll create it using the supplier and save it away. And then, of course, next time you call it, or at the same time, I'll just return it on your call every time you call it. Now, for every problem we solve, we get into a new problem. You may quickly look at this and say, aha, but this is not thread safe. Yeah, it is not thread safe. You can put more effort to make it thread safe. When you're done with all that effort, you'd have created what something like Project Lombok provides for you. But you can start with those kinds of steps. How would I use this little code now? What I can do here is, let me illustrate why we may want to do something like this. Notice in this case, it did not call the compute method. I've not made the change yet, but notice now it's calling compute. But the problem with this code you saw here is, if I were to call the get method one more time, let's say plus over here, and then I'm going to say compute of, or rather temp.get rather, you will notice that the compute is being called twice, which is nasty. You don't want the compute to be called twice. How do we really help it right here? So I change it to lazy of integer temp is equal to, and then I'll do a lazy of new lazy, and I create the lazy object, wrap this through this object right here, and now that I've created a temp over here, I'm going to come and call the temp over here. Let's make sure it's working fine for the first case to begin with. Well, that's a little bit of a warning up there about unchecked exception. Ignore that for a minute and look at the output. At the very bottom, you notice it says path 2. That's a proof that the compute was not called at all in this case. On the other hand, if I were to change it to a 3, you will notice in this output that it says called, but notice the called is called only once and not twice because it caches the result for you, and that's basically what you're seeing here. Maybe I'll fix the warning really quickly here, and then we'll move forward. So in here, I could say this is going to be a lazy of a T, or just the little angle. There we go. So you can see that call was called just once and not twice. On the other hand, if I were to say that I'm using just the x is greater than 5, you can see that it was never called in this case. So we can perform this kind of optimization in code by making sure it's never called more than once. So the moral of the story here is we can attain laziness by doing some extra work in our code. So if laziness is something you really want to support, once you get a hang of it, Lambdas can come to the rescue. Now you may argue, well, okay, but we could have done this even before Lambdas because Java had anonymous inner classes for a very long time. Then why didn't we really do it? And the answer is very simple. When the code involves a lot of ceremony, we normally don't do cool things. Because what is ceremony? Ceremony is what you have to do before you get to do what you really want to do. And ceremony really makes the code very bloated. It becomes very verbose. In this process, we lose sight of what we are really trying to do. So even though these ideas could have been done earlier, we very rarely really exploited some of those because conciseness really makes things easier for us to approach some of these ideas very nicely. So we saw how we can postpone evaluations. Like I said, laziness comes in most languages using lambdas, because lambdas give us deferred execution. That is one of the coolest things about lambdas. So lambdas offer a deferred execution of the code, and this is very valuable because deferred execution means we can postpone evaluation until we no longer can postpone it. Let's entertain this thought a little bit further to see how we can actually benefit from this. Now, let's talk about collections of objects for just a minute. So to understand this, let's go to a person class for a minute. In this case, the person class has a name, a gender, and an age. And you can see that I'm storing the name, gender, and age right here. Then I have a name, then I have an age, and a gender being returned. So it's a pretty simple code, as we can see. Let's give it a try with a slightly different example here. But I'm going to start writing the code in the imperative style first. Then we will write the code in a functional style and see why one is more exciting than the other. And then we'll come back to discuss about some of the merits of what we are doing. But before we do, I need to create some people object. So let's create some person examples here. So notice I have two Sarahs here with the values of age and gender. I have a Bob, a Paul. I got two Jacks here as well. Let's make this Jill about 42 right here. But let's say I'm interested in getting the name in uppercase of the first female older than 30. So how do I do this operation of first female older than 30? So print the, let's say, the name in uppercase of the first female, let's say, older than 30. Well, how do I write this code in imperative style? Well, the first thing you're going to do probably is you're going to iterate through this collection of people. So create people. So what's the first step? You say list of person. You'll say people is equal to create people. Well, that's a first step. But you got to start iterating over the values, isn't it? So you say for int I equal to 0. And then you say I less than people dot, is it size, is it length, is it count? You have to figure those out. In this case, it's size. Then you have to do a I++. Then to add insult to injury, you got to say get and get the value out of that as well using the get I. Well, this clearly is a lot of work. This is where the imperative style really becomes a burden. But as you know, you don't have to struggle this hard. You could do something a little different. You could say for person, and you could say from people, and this is going to be person coming from the people collection. Now you have a person on your hand. Then what are you going to say? If the person dot get gender is equal to gender dot female, let's say, and I will say over here, a person dot get age is going to be greater than 30. Hey, that's great. Now we can say string name is equal to person dot get name, and you can get the name of the person. But you know that you're not really done. You need to store this away. So where are you going to store this? You're going to say selected name is equal to, put the value into a name. Obviously, the question is, what is selected name? We'll come to that in a minute. But you also have to remember to break out of this. Because if you don't break, you might actually get the wrong person in the collection because the goal was to get the first person, not any person. So the break is extremely critical. Without it, we'll get the results wrong. But what is selected name? Well, you're going to go up here and say a string selected name like this. We may get an error. We'll work through it in a minute. When you're done with it, you want to print out the selected name. Unfortunately, though, in this code, when I try to compile this code, what does it do? It says selected name might not have been initialized. So what are you going to do right now? You will walk up to this code and say equal to null. How do you feel about it? That's not very pleasant, isn't it? Null is a smell. And when you write code like this, it becomes very unpleasant. But unfortunately, this keeps on giving. It's not done. You will now come here and say, if the selected name is not equal to null, that only gets worse, isn't it? Then you print the name. Otherwise, you say over here something like no one found. When you run the code, of course, it says Paula is the result. But I wanted the name in uppercase, so we could say dot to string uppercase to uppercase right here. And of course, that becomes a Paula in uppercase that got printed. But we know one thing about this code, though. And that is, in this code, you will never execute more work than you really have to do. So let's ensure that's really true. Let's prove it. So if I go to the person class right now, and in the getAge, I'm going to output age for, and we will put the name right here. Now, once again, if you go to the code, notice we have Sarah, who is less than 30, then the next Sarah, then Bob, then Paula. Well, Paula is the first female who's older than 30. The code will never execute, never process anyone after Paula in this example because of the break that we put. So Paul, Jack, and Jill will never be processed in this code. Let's make sure that's actually true, and absolutely that's true as we can see from the example. Well, this is the imperative style code. I'm going to comment out this. We'll come back to this later. But how do we write this code in a more of a functional style? So I'm going to say functional style. And for the functional style, how do we write the same code in functional style? We'll take the people collection given to us. We'll produce a stream on it. So what is a stream? A stream is an internal iterator in Java 8. A stream gives us the ability to traverse through the collection of objects. I'll be honest about it. The stream is what really tilted me towards Java. I was one of those guys who was constantly complaining that Java sucks. I'll be in conferences and I will tell people, Java sucks, don't use it. I used to get hate mails from people saying, why are you so evil? Why do you hate Java? And I would say, because it sucks. I'm sorry, I cannot change my words because of that. And I remember Java introducing Lambdas. And I'll be, again, very honest about it. I said to myself, what's the big deal? I've used Lambdas in a lot of different languages. I've used Lambda in Groovy. I've used Lambdas in Scala. I've used Lambdas in Clojure. What's the big deal? And I remember flipping through the examples of Java introducing Lambdas. This was about 2.5 years before Java 8 was released. And I literally stood up the minute I saw Stream because that made all the difference for me. And that is, streams actually provide a lazy evaluation. And this is phenomenal because when you're dealing with enterprise systems, you just don't want ability to write code expressively. You want performance as well with it. Let's understand what that means in this example. So I got this internal iterator. Then I say filter, given a person dot, what did we say? The gender is the first thing we ask for here. So we'll say get gender is equal to gender.female. Then I say dot filter. Given a person, I'm going to say person.getAge is greater than 30. Well, the next step here is to perform a map operation. So a filter selects the objects we are interested in, and the map says, given a person, I want to get the person.getName because I'm really interested in the name of the person. We can reduce this a little bit by saying getName is going to be the method I want to use right here. Then you can say map again, string to uppercase, and you convert this to an uppercase character. Once you do this, then you can say find first to get the very first element out of this collection. And then you can say or else, you can simply say no one found and get the first object or no one found out of this. And then, of course, that becomes the result that I'm interested in printing out. Before we execute the code, let's revisit the code, this one, from the code in the top we just saw. Notice the code in the top. You first said, check the, take the person, get the gender, get the age, get the name, convert to uppercase, break out of the loop, and control the looping all by yourself. On the other hand, look at the code in the bottom. The code begins to flow like the problem statement. This is one of the reasons why I truly like functional programming. And I came from decades of programming in imperative style. I used to program in imperative style all the time. And when I started programming in functional style, it was really hard because it was very different from what I'm used to, what I'm familiar with. But then I realized something along the way, and that is imperative style. So imperative style has accidental complexity. So that's one of the things is accidental complexity. On the other hand, functional style has less complexity built in. So this is one of the reasons why I really like functional style of programming because it has less complexity built in. Here's a little exercise for you to try. Go to somebody who understands the programming, put the code in front of them, the imperative style code that is, and ask them to read the code and tell you what the code is doing. But sit in front of them and watch their eyeball movement. It'll move like this, right? They go up and down in the for loop. At some point, it does this. That's called the point of confusion because they don't know what the code is doing. But you look at the code in the bottom. The code in the bottom is a single pass-through. Given all the people, get me only the female from the collection, exclude the male, get me people who are older than 30, get their name, convert to uppercase, get me the first one. Notice how it's just a single pass-through. I did this experiment the year Java 8 was released. I always kept saying, functional style is less complex than, has less complexity than you have, well, if I know how to spell complexity, it has less complexity than the imperative style of programming, but I wanted to really see if that's true. So here's what I did one summer. I created a little web page, and I didn't tell anyone what was on the web page. I just tweeted and said, could you please go to this page and take a survey? What people didn't know is half the people would see imperative code, and the other half the people randomly would see functional code. In the imperative code, what I had was about 4 or 5 lines of code, and the result of that little code was a number 8. The functional code also was about 3 or 4 lines of code. The result was number 8. But when people went to this, I said, don't try to copy and paste this, don't compile it, just eyeball the code and key in what your response is, what you think the result is. And I left this open for about 48 hours. In that time, about 1,440 people took the survey. I closed the site after 48 hours and looked at the analysis. Well, another thing I did was, as people took the survey, when they finished taking the survey, I started displaying dynamically how many people took the survey, what the result was, and what code they saw, what code others saw. And people started tweeting back saying, oh my gosh, I'm really surprised at the results. And the results were really surprising in the beginning. But when everything was said and done, here's what I observed in the result. The first thing I observed in the result was that in the response, out of the people who got the response correct versus getting the response incorrect, I found that about 85% of the people got the imperative code correctly. Only 75% of the people got the functional code correctly. So I was kind of wondering, why did more people get the imperative code correctly? Well, the reason maybe is because people are more familiar with imperative style, not as familiar with functional style. Then came the next interesting observation. I looked at the time people took to find the right answer. And people took about a lot less time to find the correct answer for functional compared to imperative code. What that showed you is people actually stared at the code longer to find the result. But the most charming aspect of this result was, I looked at people who got the result incorrectly. And I found that the people who got the code result incorrectly for functional style got it incorrectly really quickly. The people who got it wrong took a minute more to get it wrong in the imperative style. My answer is, come on, if you're going to get it wrong, at least fail fast, isn't it? So the point really is, and somebody said you should maybe run the survey now because Java 8 has been out for a few years. Maybe I'll do that. But the point really is that the accidental complexity is less in functional style compared to imperative style code. That's one of the biggest benefits. But looking at this code, though, look at the benefit we have said so far. The first benefit is the code is more readable. So clearly the code is more readable. We can definitely agree to it. Okay, so the code is really readable, but what about performance is often the question we normally ask. So what about performance? What kind of performance are we going to expect from code like this? Now, I'm going to say that cuteness, is not sustainable. So what does that mean? Cuteness is not sustainable. Well, what I mean by that is, I'm just observing humans. What do you say when you see a very small, beautiful baby? You say, oh, that's cute. and wait until the baby becomes 2 years old. Then we're not so pleased with the kid, isn't it? Because the kid starts asking the question, why for everything? And you're like, be quiet, you're talking too much, right? So I am of this theory that cuteness is not sustainable. Usually in human life, it's 2 years of your life, right? After 2 years, you're not that cute after all, right? Everybody says, be quiet, you're talking too much. Well, we want performance and not just cuteness. Just because the code is expressive, just because the code is beautiful, just because the code is understandable, we cannot convince the world this is a better way to do it, so what can we do? So in other words, when everything is said and done, performance is highly critical. So without having performance, we cannot really justify any particular solution because we really need the performance. So the question is, how does this code really perform? To answer that question, we need to really understand laziness of evaluations. So what does it really mean, laziness? Before I talk about it, let me emphasize one thing though. Not all languages are created equal. Don't assume just because a language provides a functional style of programming doesn't mean it offers laziness. Look at languages like Groovy or also Scala without the stream, a regular collection in Scala. Or look at JavaScript, or look at Ruby, and keep going, Python. A lot of these languages give you the functional style of programming, but they do not provide for you the laziness in evaluation. And it's important for us to understand that not all languages are created equal. Just to entertain the thought for a minute, let's give it a try right here. Let's edit a little Ruby code. My goal here is not to show you that Ruby is not good. My goal here is quite the opposite. I love Ruby, I use Ruby a lot, but also it's important to understand what the consequences of what we do also. And then there are consequences to how a semantical difference emerges out of languages. So if I take an example of, let's say, these numbers right here, and in this case, what I want to do is to take the list, we'll say puts over here, and we'll take the list and we'll say filter, and what am I going to find over here? Well, I'm going to find, given an element, I want to find out whatever the element is that is going to be, let's say, even. So if I were to say, given an element, I want only elements that are even in this particular collection. What am I going to do with this particular function? We'll say find all in here, which is the equivalent of filter. It gave you 2, 4, and 6. But I want to then take this particular object and say, I want maybe only the very first value out of this, which is 2. But the question is, what is the effort this function really performed? So to understand that, let's go ahead and take this as is even. And if I say is even of e, but what is is even? I'll define a function called is even. And the is even function says, I'll take an element, a number, and I'm going to really return the value n mod 2 is equal to 0 from this call. But if you notice in this example, if I were to say puts, we'll say over here, we'll call it as called for, and then we will output the value that it's called for, which is n. Notice it was called for every single value in the collection. Now, if I had done this in the imperative style, you'd have done a break to get out of the function very quickly. So the question is, what if this collection were 1,000,000 elements and not just 6 elements? Well, then you would end up doing a lot of extra work, which you may not really want to do. So we have to really ask the question, what is the performance consequence of this? This is where streams in Java come in. So what do streams in Java do? I'm going to say that streams in Java share a character that I've seen only among my children. I have teenagers at home. If you have teenagers, or if you were a teenager once upon a time, you know what I'm talking about, right? Teenagers are fundamentally lazy. They don't do anything until you really prod them to do things. So I've seen this at my home. My wonderful wife will tell my son, turn off the TV. It's like no words were spoken in the room. Nothing happened. The TV is still on. Then she says, put the trash out. And the trash is still there. No muscles were really moved. Then she says to him, do your homework. Nothing really happens. He's still sitting there watching the TV. Then she says, I'm calling daddy. And everything works after that. And this is exactly how Java Stream works. So they could have renamed this method as call daddy, or call mommy, depends on the house. I always say parents play this role of good cop and bad cop, right? My wife plays the role of good cop, I play the role of bad cop. So anytime I'm calling daddy, things get done. Until then, they take her for a ride. And then she is absolutely kind to them and says, could you please do it? Could you please do it? And you just throw a stare at them, everything gets done after that, right? So the point really is that all these methods are just accumulated and never executed until you meet a terminal operation. So to understand this, let's think about what kind of methods the streams have. Streams have two kinds of methods. The first type of method streams have are called intermediate operations, and then have what are called terminal operations. So the intermediate operations are absolutely lazy. They postpone evaluation until you hit a terminal method. Now here's something to keep in mind. A stream does not evaluate a function for each element. Instead it evaluates a collection of functions for each element, but only as necessary. This is a really important departure from how processing actually happens. Stream does not evaluate a function for each element. Let me qualify what that very first line really means. If stream evaluated a function for every element, what it would then do is it would take this collection here and it would quickly run this function for every single element. No, it doesn't do it. Instead, it evaluates a collection of functions. So it takes these functions and does what's called fusing. So this operation of fusing takes these functions and rolls them into a collection of function in one shot. Once it rolls into a collection of function, it says, I'm going to take that collection of function and I'm going to evaluate that function for each element, but only as necessary. So it doesn't run off the rails and start running everything immediately, eagerly. It waits and postpones it. Let's see this in action to make sure this is actually true in the evaluation sequence. This is probably one of the most important things for functional programming is efficiency of code, because laziness really means efficiency. So how do we get that in this code? Let's give it a try right here. Let's go back to this code and say, I want to print out the get age as we run through this code. Let me go back over here and execute this code right now. And notice the evaluation said age for Sarah, Sarah, and Paula, but it never really touched Paul, Jack, and Jill. And the reason for that, similarly, just to convey that it really is doing the things lazily, let's go over here to the getGender function. And in the getGender function, similarly, let's output, let's say, gender for, and we will say the name, and evaluate this code one more time. Notice it got the gender for Sarah and age, gender for another Sarah and age, gender for Bob, and gender for Paula, and age for Paula, but it never touched Paul, Jack, and Jill, and that is because it rolls these into a collection of functions, which is the fusing, and evaluates it per element, but only as necessary. The minute you hit the find first, it bails out and says, I don't need to run this anymore. In fact, let's look at this slightly differently. Let's go back to this code right here. Let's leave this up to this point, and I'm going to say output done right here. When I execute this code, notice that it printed all that result and said done in the very end. However, if I go back and comment out only this one right here alone and nothing else, now what's going to happen? Notice we have all these intermediate operation here, but we don't have the terminal operation. So as a result, when we execute the code, it simply says done. It never actually evaluated any of those other functions. That is absolute laziness, as you can see. This is kind of like what you see at work, isn't it? You're sitting at work in the morning, one of your employees comes to work, looks around and says, hey, where's the boss? Oh, the boss is sick today. Yes, I don't have to do any work then today, right? Well, because there's nobody to really monitor and get the results out, why bother doing the work? This is exactly what I mean by laziness. This is like back in school, we may remember the days. There were two kinds of kids. The kids who study all the time, and the kids who study only the day before the exam. You know what kind of kid I was, right? Those people who study all the time, they're called losers, right? Why bother doing it? A lot of things can happen between now and the exam. There could be a storm on the day of the exam. The teacher may die before the exam. A lot of things can happen, right? Postpone it until I'm just kidding, of course, but the point really, but only lightly. But the point really is that why really do work when you don't have to do the work? Let's make sure the result is really needed and then do the work. That is laziness. Well, there are a couple of consequences of laziness in the code. We cannot just assume laziness can be had for everything we do, because laziness hinges on some very important ideas. Let's revisit them and talk about that real quick. So we said laziness, but let's revisit functional programming. When people talk about functional programming, they often talk about two things which is necessary but also frustrating. The two things they talk about are immutability. So how many times have we heard this over and over? We need to honor immutability, they say, right? So immutability is extremely important. The second thing they talk about is higher order functions. And sure, higher order functions are very important as well. So in functional programming, we honor immutability and we design with higher order functions. However, to me, these are not really the most important things. I would say the above are means to a greater end than being the end themselves. So when I talk about functional programming, I don't want to really talk about themselves. I don't want to talk about immutability and higher order functions to begin with, because those are extremely important, but that's not what you're really doing functional programming for. You're not doing functional programming to honor immutability. You're not doing functional programming to use higher order functions. These are tools of the trade. These are things you use, but there's something even bigger and greater that you're really after. So what is that bigger end that you're really after? And that bigger end is, what are those? The first is functional composition. Functional composition is one of the most important things in functional programming, because functional composition reduces complexity in code. Notice this function composition right there. We said, I want to take the collection of people, I want to filter the people with the particular gender, I want to filter the people with a certain age, I want to get their name, a transformation, transform again to get the uppercase, and then find first. That's functional composition. If you're interested, Google for this. Martin Fowler talks about this as collection pipeline pattern. So that's what he calls as functional composition. As his name he gives is, so functional composition, he calls it as the collection pipeline pattern. The collection pipeline pattern is a very compelling pattern. We've been programming decades with for loops and while loops. Moving forward, as we embrace functional programming, we'll really start using this functional composition or the collection pipeline pattern more effectively. That's one of the most charming features that you're going to look at when you get used to it. The second thing in this here is a lazy evaluation. So functional composition and lazy evaluation are the two most important things behind functional programming. But make no mistake, without immutability, you will not be able to attain lazy evaluations. That is something we have to be very careful about, because without immutability, laziness doesn't really make sense. And if you are not willing to provide immutability, you are going to be in a bigger trouble with languages that implement functional style of programming. This is something we have to be extremely careful about. To illustrate this point, let me bring out a slightly different example here so we can understand why laziness cannot survive when immutability is not honored. Because programmers often, moving from other paradigms into functional style, are used to one way of programming. Functional programming came from languages that predominantly enforce immutability. And when you are in a language which enforces immutability, it's a lot easier to do functional style. When you work with a language that does not impose immutability, we as programmers are at higher risk, because we're using a wrong tool for the wrong job, and if we don't understand the consequences, things can go haywire. So to illustrate this point, let's take a slightly different example. Let's say for a minute we have a list of numbers, and I'm going to just start with the list of just few numbers right here. Let's say 1, 2, 3. And given these numbers, I want to say in here that numbers.stream, and I will say .map, and given an element, element times 2. And let's just save this away into a stream of integer. We'll call it stream is equal to. So I just saved away this stream right here for now. Then I'll come down here and say stream.forEach and system.out println, and we will just print it. So when I print this out, what am I dealing with right here? Let's go ahead and bring in the stream real quick. And when I run this code, it printed 2, 4, and 6. What is this we are dealing with right here? This is lambdas, right? So we'll say lambdas. So we have a lambda on our hand. This is a lambda expression, but I'm going to say lambdas are stateless. This is one of the first things to keep in mind. Lambdas don't have any state. Notice this lambda. It takes a value e and returns times 2. It carries no state with it. So the input is e, coming in as a parameter. The output is e times 2, but internally it has absolutely no state at all. That's what a lambda is. Lambdas are stateless. On the other hand, I'm going to go ahead and say in here, int factor is equal to 2. Notice I make it as a final int factor. Well, a factor is 2, and I'm going to say this is factor. This is no longer a lambda. So what in the world is this then? This is called a closure. So what's a closure? A closure closes over the defining scope to bind it to variables. This is why it's called a closure. If you are alone in a dark room, say the word close over many, many times loudly, you will begin to realize you're saying the word closure. So closure is nothing but close over, right? So close over is closure, and a closure is going to close over a variable in its defining scope to bind to a variable. Well, closures carry state. So lambdas are stateless. Closures carry a state with them. Now think about it this way. Let's understand what this really means in this context. I want you to just think about the call stack for a minute. You are in main right now, which means you're a call stack level 1. You are calling the map method. You're in level 2 of the call stack. Here's a way to think about it, right? I'm here on ground floor, right here on the ground. That's level 1 of the stack. I call the map method. I'm on the level 2 of the stack right now. So I'm here, and I'm not trying to climb on this one. That's not civil. But imagine I climb one more level up. Oh, here you go. I'm in level 3. So when I'm within the lambda, I'm in level 3 of the stack. Can you imagine now? What is factor? Factor is on level 1. Where am I needing it? I'm needing it in level 3. It's possible you pass this to another function as well. You could be in level 4, level 5, level 6, who knows? And I'm saying, from here, I'm going to somehow reach down all the way to level 1 and grab that variable from there. What do you think? Is that possible? I'm short. Definitely not possible, right? And that's kind of nonsense. That's not going to happen. Well, if that is the case, this is not reaching its hands from level 3 all the way to level 2. How in the world can this use factor? And the answer is very simple. It carries it with it. Here's a way to think about it. Imagine I believe in eating healthy meal. And I'm at work, which is 10 kilometers away from home. At noon, I'm hungry, I want to eat. Wait a minute, I'm not at home. I know home has healthy meal. What do? Oh, Venkat, very simple. Pack your lunch in the morning when you go to work. So I carry my lunch with me. At work, I'm doing the work, but I'm hungry. I eat my lunch I brought from home. In other words, that is lunch from home. So in other words, when this lambda is created, that state is packed into it and is carried with it. I'm going to emphasize closures carry, and this is very important, immutable state. Because if you carry mutable state, it's a disaster in the making. And I'll show you why that's so important to be very careful about it. I'm saying that laziness is cool, laziness is important, laziness is vital, but you cannot get laziness for free. There are things you have to do to attain laziness. In languages like Haskell, laziness is easy because the language enforces immutability. Haskell will not tell you that function should be pure. Haskell will tell you function should be pure. It'll follow you home. As you're eating your meal, it sits and watches you and says, I know what you're thinking, don't do that. And it watches over you every step of the way. Java is like a nice friend. It says, you know what? You shouldn't do this stuff, and walks away. It doesn't belabor. It doesn't come home and haunt you. So Java is not going to enforce it. But keep in mind difference between languages. One hand, Haskell will enforce it. It will say, I will make sure you don't do this. Java is like, I suggest you don't do this. Now, programming in Haskell is boring. Can you imagine the life of a Haskell programmer? Go to work, you start programming, 10 a.m., everything works. And you're like, what do I do? I'll take a long lunch. You come back from lunch, you code again, 5 o'clock, everything works again. You go home, you walk quietly into home, the family says, how was day at work? Life as usual. I wrote code, it worked, I'll go back tomorrow, do some more work. Java, on the other hand, is fun. Because Java does not expect things are immutable. It assumes it's immutable. What happens when languages assume things rather than enforcing things? When a language assumes things, and when you disagree with the language, who wins? The language does, right? So in the case of Java, you go write code, and you forget that it assumes immutability, and all kinds of things fail. And you're sitting there and debugging until late in the night. And at night, you say, I'll come back and continue tomorrow. And you're tired, you go home. And as you enter, the family says, how was your day at work? You're like, let me tell you the stories, right? Because we got stuff to talk about now. And this is what I did. When you grow up, make sure you never do this, right? Well, the point really is, this is something you got to know, otherwise you're in trouble. Let's see why. Let's go back and take a look at this code real quick. I want to go back and say that factor is equal to 2. Just like that, factor is 2. Well, keep in mind, I declared this as final. Because it's final, I cannot change it right here. You know that very well. Notice where the error comes from. Line number 16 is where the error is. Line 16 says, are you out of your mind? You're trying to change a variable that's final. Oh, sorry, I won't try to do that. Now notice, I go back over here and remove the word final. This is called effectively final in Java. So what is effectively final? Effectively final means you don't have to declare it final, but you treat it like it's final. Java says, you and I have been going out for 20 years together, we can have a little understanding. You don't have to say it explicitly as long as you behave like we are in relationship here. So that's exactly the point. You don't have to really put final, but treat it like it's final. Notice when I run the code, it didn't complain at all. However, I now say factor is equal to 2. Now what happened? Java says, aha, you made a change to factor, even though you said the same value doesn't matter, which means this was not effectively final. You didn't mean this to be final. At this point, the Java compiler says, hey, programmer, let me help you a little bit. Please don't do this. Notice the error, where the error is. Error is on line number 11, not on line number 16. So error is on line number 11. Why did the error come up on line number 11? The reason error is on line 11 is the lambda right now, the closure right now is not pure anymore, isn't it? The closure is not pure. Why is the closure not pure? Because the closure now is depending on and carrying a mutable state. It's carrying a mutable state because this state that you are carrying with you might change eventually. When the state is mutable, The result of this is unpredictable, and so Java says, please don't do this. However, you know how some programmers are very dangerous programmers? They will have a very villainous smile on their face, and they will look at you and say, I know how to work around this. Generally stay away from those people, right? Very dangerous programmers. But the programmer rolls the sleeves and says, let me show you how to do this. And what does the programmer do? Puts a square bracket here and says, new int square bracket 2, and they pause and smile at you, right? And then they say square bracket 0. And then they come here and say square bracket 0. Now, when you run the code, notice the code did not complain. Don't mistake that Java doesn't care. Java is in a state of shock right now. If you deeply look at your Java C compiler, it'll be shaking like this. Because it's thinking, who are your parents? How did they raise to be like this anyways, right? That's what it's asking. This is really bad programming. We should never do this. Why is this such a bad idea? Because the question to ask here is, if I modify this code to 0, and now I'm going to run the code, and I'm going to ask the question, what is the result? How many of you think, and don't worry about being wrong, I'm wrong most of the time myself. How many of you think the result is going to be 2, 4, and 6? A few people, okay? How many of you think the result is going to be 0, 0, 0? A few people. How many of you say, I don't have a clue? I love it, right? Absolutely. That's the right answer. I don't have a clue. In fact, I use this as a very favorite interview question. I will push this on interview and say, what's the answer? If the candidate tries to answer the question, they are fired before they are hired. Because the right answer is, are you all stupid? That is the only right answer. Because I don't like to do Java puzzlers at work. I want to write production code. Writing code like this, you're causing problem for everyone in the company. It's not about what you write, but what you leave behind for others to maintain, right? This is incredibly hard to maintain. Never allow this. When you run the code this time, the result was all zeros, as you can see, but that's because of lazy evaluation. Java will perform lazy evaluation all the time when it comes to streams, and if you're mutating data, the results can be really hard to debug, really hard to understand, really hard to reason. This is bad code, don't write it. In fact, I want to emphasize, please don't do this. So this is something important. Don't do this because this is impure code. Impure code is really hard to maintain. So I get emails constantly. The email starts with something beautiful that says, my code worked fine until yesterday. I'm like, I know exactly where we are going. And then today we turned this code into parallel and things are not working, can you help? And I will immediately scan through and say, oh, there you go, you're mutating the variable, that's why. At work one day, I walked in the client side and my client said, the code ran really fast. And paused. I said, and it gave you the wrong result, didn't it? He's like, yeah. Okay, I know where the problem is. We are mutating something, and a closure is depending on a mutable variable. So that is something very important to keep in mind. You cannot do a couple of things. So, in other words, immutability and laziness are mutually exclusive. So you cannot really bring them together. You cannot really have them together. Sorry, mutability, not immutability. Mutability and laziness are mutually exclusive. So you have to honor immutability because with mutability, you cannot have laziness. You can either have mutability or you can have laziness. You cannot have both. And unfortunately, language like Java will only try to protect you a little bit. It's not going to come home and stay with you and say, I'll make sure you don't do this, right? Its moral campus is not that big. It simply says, I'll tell you what to do, but you be a grown-up after that, and this leaves you alone. So you have to be very careful about it. Having said this, we talked about laziness in collections, but if you honor immutability and enjoy laziness, there are some benefits you can beautifully get to. And so before we talk about it, let's talk about immutability one more time. So what does immutability give us? Many benefits. You get many benefits. I'll just list a few benefits here, and then we'll talk about the other one. Many benefits. The first benefit you get out of this is that the code is easy to reason. You can use referential transparency. That's another benefit. You can use memoization. It's easier to test. And then, of course, you can have lazy evaluations and easier to parallelize. So these are the benefits you get out of immutability. So when you honor immutability, the code is easier to reason. Code can have referential transparency, some optimization techniques, memorization to optimize. A lot of these lead towards better performance. Out of these, maybe 6 of them, 3 of them are related to performance, right? Well, that's related to performance, that's related to performance, that's related to performance. Sorry, 4 of them are half by 1 error, lazy evaluation as well. But lazy evaluation itself leads to efficiency, but it also opens the door for infinite streams. And this is one of the things I really love about laziness. The minute we get a hold of laziness, we can enjoy something even better, which is infinite streams. So let's understand what that means by infinite streams. So quickly, let's take a little example and play with it. Let's say for a minute, I'm interested in doing the following. I'm interested in creating, find the total of double of square root of first k prime numbers, let's say, starting with n. Whatever that n is, we don't know what that n is. So total of double of square root of k prime numbers starting with n. How do I know if a number is prime? Let's go ahead and write this. So we'll say Boolean. And in this case, we'll say Boolean, is prime, given an integer n. All I'm going to do, without regard to efficiency here, return number is greater than, let's say n is greater than 1, and int stream dot range 2 to number, and we'll say none match. So in this case, of course, given an index, we'll say n mod I is equal to 0. So this gives us an ability to find if a number is prime. We'll bring in a stream. So that's is prime. But how do I really write this in imperative style? Well, in the imperative style, what do you normally do? Let's give it a try. I'll call it as compute. We will pass a 101, and let's say k is 257. Some random numbers I'm going to give to the compute method. Let's write the compute method. So public, what do we do here? Static. The result is going to be a double, compute, int n, int k. So given this number, n and k prime numbers starting with n, how do I write this code in the imperative style? We'll get to this in just a second. Make sure the compiler is happy. None may tch. So what am I going to do with this? Let's give it a try. Int index is equal to 0. That's the very first thing you do, isn't it? Then what do? Int count is equal to 0. Double result is equal to 0. So what did you do so far? Spent your time defining a lot of things called garbage variables, nothing useful. Once you're done with this, what's the next step? You say for, and in this case, you want to start for that many count, so you can say while count is less than k. At this point, you come to a screeching halt and ask the question, is it less than or equal to? Do you ever ask that question? Every single time, isn't it? If anyone asks you, what's the purpose of this operator? There's only one purpose for it, to make us feel stupid. Because every time you type it, you pause and say, huh? Is it less than or equal to? You're never sure about it, isn't it? Then what do? Then you say if e is prime of index is true, then you say result plus equal to, and then you want the double of the square root, isn't it? So math dot square root of index times 2. And then once you do it, you add to that value and you return the result. Well, the question is this correct? And you notice, no, it's not correct. You need to increment the index. Oh, of course. Let's go ahead and increment the index plus plus. Is it correct? Oh, you have to increment the count plus plus. Is it correct now? You say, no, it's got to be outside. Okay, we move it to the outside. Then you say, no, this has to be inside. How do you feel about that? That's a lot of complexity, isn't it? You look at this code and you're like, wait, let me figure out what the code is doing. That's the ugliest word in English. Let me figure out what the code is doing. I don't want to figure out. I want it to be obvious what the code is doing. I don't want to be figuring it out. So when I run this code, what is the result I get? Some result. I don't know if it's correct or wrong, but that's what it gave us. But that code is quite complex, isn't it? What can we do about this? How can we make this a little simpler? Well, remember this right here, less than k. Why am I doing that? Why am I hitting the limit and checking for that? Let's try to write this using functional style. So what am I going to do? I'm going to say return stream.iterate. What am I going to start with? N. Given an element, element plus 1. Just stop right there and look at this. That's called an infinite stream. What is an infinite stream? Infinite stream has no bounds whatsoever. It starts with n plus 1, n plus 2, n plus 3, n plus 4, n plus 5. Keep on going. I know what you're thinking. You're thinking, oh my goodness, if this is infinite stream, where will you store it? On the cloud, of course. But the point really is that this is infinite, has no bounds to it, absolutely, isn't it? Then you say dot filter. Given an element, I want to know sample is prime. Only get me the prime numbers. Then I perform a map, and I want to take the number given to me, and I want to take the square root of it. So math, and then call it a math square root, and find the square root. I'll say map to double. But I want to double the value again. So we'll say given an element, element times 2. Then what do I want to do? Limit k. And you may say, wait a minute, is it k? Or less than k, or less than or equal to, it's k, damn it, keep moving. No need to waste your time, right? And then you perform a sum operation on it. When you do this operation, that result you get right there, what did this do? You start with n, but you built an infinite stream. Then you found only prime numbers from it. Then you got the square root of the values. Then you doubled them, and you found only k of them, not everything, and then you totaled it. Notice how expressive the code is. But of course, this code would not be possible if this was evaluated eagerly. Because eager evaluation of that would result in creating an infinite series, really, but you don't want to. The infinite series, the trick really is, the series is infinite, but it only creates it on demand. It's like pay-per-view. Only when you ask to view it, do you pay for it, and you get it. So in other words, it generates only as many elements as the limit says we should be generating, and not anymore. Laziness leads to creating infinite streams, an idea we're not so used to in languages like Java, because we haven't had this ability to be lazy, but now that we have the ability to actually create laziness in evaluation, we can exploit some of these ideas much more, because we never really enjoyed these ideas before. As I was writing the book on Java 8, it dawned on me that I can implement tail call optimization, which doesn't exist in Java, but I can implement it using infinite streams. Ideas like that can be exploited now that we know that laziness is possible. And laziness leads to that capability of creating infinite streams, which means there are a slew of algorithms that we only talked about in the past, but never were able to really implement so easily in language like Java. We can definitely do that. So to me, one of the most charming features of functional programming is really the laziness. Because the real excitement in functional programming is not just the cuteness of the code, where you can remove the accidental complexity, but the efficiency that comes with it as well. I don't think we can really survive with a readable code alone. We need efficiency too. We cannot survive with efficiency alone because we need readable code as well. That's the combination that we are really getting. Because in the past, we were able to write code that's efficient, but horribly hard to maintain. With functional programming, we can get the best of the both worlds. In a way, it's kind of like having the cake and as it eat it. We can write code that's readable, code with less complexity, code that is maintainable, but a code that is also efficient in performance. And of course, if you really want higher performance, you can go parallel if you want to. Parallelization is easier when you have a functional style with immutability. You can also do laziness and get the performance gain as well. Depending on what you're trying to do, you can gain performance one way or the other. And that's what we just did. We used the sequence generator to create it, and we saw how that leads to efficiency. So to summarize what we talked about what laziness is. We talked about how some languages are built naturally to be lazy. We talked about how lambdas are a gateway to become lazy, because lambdas are providing a level of indirection, and by doing so, we are able to design for laziness in our code. We talked about how some languages provide laziness while others don't. But one of the core strengths of functional programming is laziness. Without it, doesn't really make sense to really rely upon it. and we saw how laziness can lead to many good things, including how we can create infinite streams and we can benefit from that. I hope this was useful. Thank you.